start the recording now. And now we are now we are complete, I think. Okay. We learned that forward biasing squeezes the space charge region. It counteracts the electrical field. Thereby, it reduces the barrier. And the Boltzmann statistics say that the amount of electrons which are above the barrier, which can diffuse over the space charge, increase exponentially, and therefore we have now an electrical current. Let's talk about that current. First, we talk about the so-called flow lines. What are flow lines? Assume that from the P zone, the holes are alongside these flow lines, and the electrons from the right-hand side in the n-type semiconductor. What does this sketch mean? At the contact area, the complete current is carried by the holes themselves. At the contact area, in the n-type, the complete current is carried by the electrons themselves. But in between, there is changing something. So you know that we inject electrons here. What does these electrons do here? They do here change the concentration of the minority carriers. Let's go back. You see here minority carrier. If you flood electrons in this area, you change this minority carrier concentration, you inject a delta N. What we have learned about this injection? We learned that this concentration, which is not N0P, it is above with delta, it diffuses away. Okay, and this excess concentration, these additional electrons, do generate an additional recombination. Now, this makes the following. So the electrons, which, let's start with the holes. The holes which are injected, they have the chance to travel alongside until they find an electron and they recombine. And these concentrations change as a function of the distance. So we assume that the electrons which are injected from the right-hand side also diffuse and recombine, diffuse and recombine. And what we assume in addition is that within the space charge region, no recombination takes place. We will learn a little bit later why this assumption is roughly valid. From this sketch, it is not very obvious why this recombination does only take here, but not here. Okay, and you see that the hole concentration, the p-type doping, is larger. Why? We have more holes to be injected here compared to the electrons to be injected here. Okay, but what we see at each and single location, the number of flow lines is constant. That means the current is constant. It doesn't matter whether the current is carried by holes or partly by holes, partly by electrons, or completely by electrons. The current is constant. Okay. Now, oh, I there is missing something. I see now. Dum 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 dum. This arrow. Okay. Whole flow, electron flow. So let's continue. I have put together equations. These equations should talk something to you. Let's put their sense together. I am not on the equations themselves. I am on the sense of these equations. The minority carrier concentration, we take here at the boundary, at the left-hand side, and at the right-hand side. And then we take a closer look what happens with these concentrations in the P region and in the N region. Now, first, what are the majority carrier concentrations for the bulk semiconductors? Bulk semiconductor. So here and here. What are they? They are NA, and here ND. But you can also express this by the Fermi level. But because this is the same expression, so the concentration is given by the intrinsic carrier concentration. So the table we have referred several times by the distance of the Fermi level to the intrinsic level. Okay. Let's keep this. Let's keep in this P region. The N region is equivalent. Okay. Now, what are the minority carrier concentration at zero bias? At the space charge boundary, where at zero bias, here. The minority carriers, we know them also. We have learned that. That's the mass action law, or so mass impact law. Oh, that's really, it's really good. All these videos on YouTube. So everybody who takes a look at the video knows that I cannot remember this word. So mass impact law. The minority carrier concentration at the space charge region boundary has a value we know from the mass impact law, or you can say it is reduced by this voltage because the built-in voltage is exactly the difference we have from the right side to the left side. One moment. Why I can say that? See here. I have here the majority concentration, right? And if I have here the majority carrier concentration, if I go with V built in up, I have the minority carrier concentration. So the same, so I can express referred to this level, this value, or to this level, this value. Or if I use the intrinsic, I can derive the same equation referred to the intrinsic carrier concentration. Let's take a look at the equations here. One moment, here. If I use the built-in voltage, I start from the majority carrier concentration and calculate the minority carrier concentration. by taking into account the energy level, which is between these concentrations we have. Okay, so let's continue. Let's take a look at the minority carrier concentration with bias, with applied bias. That's the same, but with the voltage we apply. What happens if we apply a certain voltage? If we apply a certain voltage, we separate the Fermi levels, and we change thereby this voltage, this voltage. And exactly using this voltage, we can calculate the concentration, with voltage. Okay, now let's take this equation into account. Now we don't have the equilibrium value, we have the changed value. There is no more the zero because we have applied voltage. Now I can separate this part and this part. This part. Okay? Sure. What do we see here? If we compare this value with this value, we see this concentration. Okay? So we can plug and play here. And now we have a very interesting equation. And this result is the point where I'm aiming at. The electrons in the p zone at the space charge region boundary is referred to the equilibrium value, minority carrier concentration, times e to the power of voltage you apply. And this is the important point. At the space charge region itself, so at the space charge region itself, the minority carrier concentration is the bulk concentration if you don't inject anything. But if you inject something, this value of the number of electrons increase exponentially with the applied voltage as a relation to the thermal voltage, as a fraction to the thermal voltage. This means this reduction in the barrier due to your applied voltage gives you the potential to inject electrons, and the number of electrons therefore increase exponentially V divided by Vt times N0 in this P region. This equation we have derived from here to here. As an footnote, you don't need to learn this derivative, for this explanation, how we come from here to there. But you have to know this equation by looking at least to this sketch. Okay. So, and the same game we have here, the minority carriers in the N zone in thermodynamic equilibrium is mass impact law, yeah, is given by the mass impact law, and this value is increased by exponentially by your applied voltage at the space charge region boundary, at this location. There we start. So we have the boundary conditions. What we have now? We have everything. We have the following thing, which is used and one times questioned why we have to know this. At that point, we now know this value at the space charge region. We know that. And what happens as a function of time if we switch off the current, if we switch off the voltage, this concentration drops by time. What do we know in addition? In addition, we know, one second. No, the rest we don't know yet. We will learn. We know that the flux is a function of the disturbance. You know? You know this equation? The flux is a function of the disturbance. The flux is a function of the disturbance. So we know that at the space charge boundary, we have a certain delta n, and therefore we have a certain flux. And this flux does change with the location. And these topics we put together and do some calculations. Here we are. If we take these boundary conditions and use the continuity equations, we get, starting at the boundary of the space charge, that yes, we have some injected electrons which disturb the minority carrier concentration by this value, but this value is reduced as a function of the location x exponentially, and not the time constant, but the location constant, let's say. Yes? Okay, the location constant has an own name. It's the diffusion length. Instead of the time constant, it has the name diffusion length. What is the diffusion length? Yeah, it is the length where it is drop is 1 over 1 divided by E. Okay, and you know that if you further go to the bulk of the semiconductor, you reach the thermodynamic equilibrium. The same applies. So this is the junction between the p-type, and the n-type. This is the junction. And here we inject the holes. The holes disturb the minority carrier concentration, and this concentration also drops as a function of the location. And also the time constant, the diffusion length, is given here. So what is the dependence of this diffusion length? The diffusion coefficient, sure, because the flux is diffusion constant times dn dx. So therefore we have this diffusion constant. And now we have an additional value, tau h. or tau E. Tau H and tau E are, one second, do I have it here in a written manner? No, I have forgotten it. No, I haven't forgotten it. It's the lifetime, minority carrier lifetime. So the lifetime and the diffusion constant does give us the diffusion length. Okay, it is understandable also heuristically, because if I put a lot of electrons here, I have a bunch of electrons there. Now, this bunch of electrons tend to recombine due to the excess concentration. Okay, they recombine, but in addition, they tend to diffuse. Okay, so the diffusion plays a role. If they diffuse, the concentration is lowered, and the lowered excess concentration also tends to recombine, and so on. Diffusion, recombination, both play a role for this type of exponential decrease in the injected carriers by the applied voltage. And the full equation is here. So what we know now? We now know if this is the diode and if this is the junction, and if this is the space charge region, then we know at each location the minority carrier concentration. This we know. What value does it have? It has at least this level, but it has additional this level. Now let's take a look to this level. It has two dependencies. One, it has a dependency on the voltage. Yes, sure, because at the boundary, the level is given. That's the boundary condition. And if we are not at the boundary, but if we are within the semiconductor, then it depends on the diffusion length, which is given as a factor of this minority carrier concentration. Now, let's go to, now you take a look to this sketch, memorize it. Now let's go to my Excel sheet again, because I have plotted that stuff also. Because no equation makes sense if you can't see the results. Before we go there, I'm looking at the voltage level. So 0 volt, you see? 0 volt. Okay, let's make an 0.4 volt forward bias. You see, you see here 0.4 volt forward bias. The space charge region is reduced. Now let's take a look at the concentrations. This equation and this equation. So these two equations I have plotted here and here. And you see that these equations it's not updated. Now it's updated. Now it's okay. Now it looks similar. Let's make the doping concentrations also equal to both sides. So we have the sketch relevant to the slides you're seeing. So the concentration is 1 10 to the power of 16, 1 10 to the power of 16. Now let's go back to Yeah, you see the space charge region is now symmetric. Here, it's symmetric. It is decreasing with an exponential value. The electron density, the, the hole density is also decreasing, but we don't see what I have given you in my sketch. You don't see this space charge region. You just see this and that. Why? Because I have put you onto a lie in the sketch. You see the scale of the space charge. The space charge scale is 100 nanometer or so. What is the space charge? Let's see. The space charge region width. One moment. It is calculated somewhere here. TV 224 nanometer. You see the value there? Okay. Nanometer scale in the space charge region. But I'm waiting for my Excel sheet. Makes me angry. In the micrometer scale, you see the diffusion length. And if I zoom in, I try to do that. Do you see these dotted lines? You see here some dotted lines, perhaps. I just zoom in 400%. More, it's not possible with Excel. Yeah, okay, no. Perhaps you can see it on your own Excel sheet. I have plotted the space charge boundaries also in this diagram, but due to the scale of 200 nanometers in micrometers, you are not able to identify this region with. And therefore, because the recombination, one moment, the recombination takes place, the concentration drop takes place, but the space charge region is here, and the diffusion length drop is something like this. Now it's in scale, okay? And therefore, I said for these flow lines, in this space charge region, there is no recombination because the probability of recombination within the 200 nanometers is zero compared to the recombination outside the space charge region. Okay, let's go back here. Now I have just taken this equation and plotted. And we have seen that we have some injection from the other side, and as a function of the location, the concentration does drop. Okay, that's great. What happens if we apply reverse voltage? I want you to calculate this factor. Assume this is 1. Where is this factor 1? It is at the space charge boundary, okay? At the space charge boundary, this factor is 1, so don't calculate it, it's 1. Please calculate at the space charge boundary the voltage induced factor which is multiplied with the minority carrier concentration. First, with 0.6 volt. Second, with minus 0.6 volt. And assume that the VT is 25.9 millivolt, so 300 Kelvin. Mhm. What we have learned now, if we apply forward voltage, we increase the minority carrier concentration by 10 to the power of 10. Okay, so this increase is also a lie. Is increase is 10 to the power of 10. And the only thing which is not a lie is the reverse voltage. Because if you minus 1 times this plus this is 0. So this point is true. But this point is not in scale. And this is also visible in, in the Excel sheet. One moment. I'm zooming back, or I try to zoom back. Has it worked? No? Okay, now we have it. Do you see the applied voltage? Yes, you see. 0.5 volts. Now I set it to 0 volt. Okay, at 0 volt, we have the minority carrier concentration, undisturbed, because no voltage. Now we apply minus 1 volt. Click. Zero. Here we have, one moment, here we have 0. And at this scale is, yeah, a large value. And it changes drastically with the applied voltage. Therefore, we have here, you see, this is the minority carrier concentration roughly. Now I apply a positive voltage. Take a look at this value. 0.2 volt, 0.3 volt, 4 volt, 0.5 volt, 0.6 volt. So you disturbed this level from 10 to the power of 3 to 10 to the power of 14. Okay? So this is what I have said. This is not in scale in my lectures. Okay, so please play around and take a look at the figures in the spreadsheet I have provided you. Okay, forward bias plus minus, reverse bias minus plus. If we reverse bias, we learn that this concentration drops to 0. Now you know also what happens with. Now we are there where you have dropped your question, Mr. Muka. You dropped me the question, what happens with the majorities, minorities? These minorities here in reverse bias condition, this concentration at the space charge region boundary is 0. The concentration in the bulk is N0 in the p-type area. And here it's 0. And in between, it is a drop of exponential curve, the concentration. Why? Assume you have a bunch of sand on your table, and this area is the edge of your table. What is the shape of the sand level? At the edge, it's almost 0. At the table somewhere far away from the edge, you have a certain level. The certain level is the N0P. And in between, you have a dropping level due to vanishing, due to drift. So reverse bias takes away all the minorities at the edge of the space charge region. And the sand comes back to this area due to this drop. That's all. Therefore, if you reverse bias, you have a certain current. 1 second, please. If you reverse bias, you have a certain current. What is current? What a flow of electrons. What is a flow? Flow is diffusion coefficient times the change. One moment. The flow is the diffusion coefficient times the change of your, let's say, electrons as a function of the location. Does this slope change if you increase your reverse bias? No, because this level is fixed by your doping. This level is fixed by 0. Yeah, that changes. Exactly, exactly. So that's the perfect moment to go back to 1, 2, 3, 4, 5, 6, 7 to reverse biasing that stuff. Now I have a reverse bias of -1, -2, -3, -4. So the space charge region here, which you don't see due to the scale, increases, but the slope doesn't change. It just pushes away. And the slope itself is defines the flow, and the flow is the current. And therefore, reverse bias changing doesn't change the slope, the current. Again, please, the beginning of your sentence. The current of a diode in reverse bias is the current of the minority carriers, which are caused by diffusion to the space charge region edge and drift to the other side. We will calculate it. Yeah, sure. We don't do much, but this we will do. And in forward bias, what is flow? Flow is the slope, the change of the concentration. The change of the concentration we will see here. Okay, so we go back to zero bias and then forward bias. We indeed take a look at the scale. We indeed change the slope. by bias. Therefore, we change the current, what we expect from our experience. Okay, so let's go back to the slides. We have learned that. Now, I have put together, just for your convenience, what it looks like for forward bias at the space charge boundary with the minority carriers, but be aware this is not in scale with this diffusion length. The diffusion length is in the micrometer scale. The space charge region scale is in the 100 nanometer scale. Okay, let's do the last very complicated, no, very easy step. The current. We know from the flow lines that at the contact, everything is defined by the holes. Everything is defined by the electrons. And what we can calculate is the concentration at the space charge boundary and going away from the space charge boundary, but for the minorities. Again, we learned the concentration of the minorities starting at the space charge boundary and going away from the space charge boundary for the minorities. And we know from the flow lines that in the bulk, everything is defined by the holes. But what we don't know is what are the flow lines for the majorities. Okay, that doesn't mind. Why? Because of the total current. Well, everywhere in the diet, the total current is constant. Sure, if you put here 1 ampere, there the 1 ampere goes out. And if the cross section is constant, then the current density is constant. Well, if we have then this current density here, we have here the same current density that compared to here. Now we have all values to calculate the complete current. How? If we know this current here, and if we have the complete current here, then the rest is from the holes. So if we can calculate the current from the minorities, we can calculate the current from the majorities because we know the complete current. One moment, I have no idea about this current level, but we know from here. Because here we can calculate the current from the minorities in the n-type. And we assume that in the space charge, nothing changes. So if we then consequently calculate the current here and calculate the current there, and then we say this is equal, then we can set a plus sign and we have the total current. Yes, the puzzle is complete. One moment, I'm talking about the current. And here I talked about the concentration. How we come from the concentration to the current? Very easy. The first derivative of the concentration times the diffusion constant is the flow. Flow of sand, no, flow of electrons. And this is the current. That's all. And the same is valid. Okay, if the first derivative of exponential function is again exponential function, and the internal function derivative gives us some values. And these additional values are given here. No, here. So we get into the current, the diffusion constant, and the diffusion length. Um, let's make, later. Okay, so we can calculate with the flow rate and the elementary charge the current density for the electrons. And the holes exactly equivalent. Now, again, now we have the current. Now we have the current, which looks exactly the same like this curve because it is a decaying exponential function, and the first derivative looks exactly the same, but with a different scale. That's it. And for the sake of completeness, I have also plotted the current densities, for the electrons, for the holes, and they look exactly the same way, yeah, sure. And the values are different. Why? Because of different lifetimes for holes and electrons. Due to these lifetime changes, due to the different mobilities of that stuff. So the mobilities are different. So different mobilities, different diffusion coefficients, different lifetimes result in different current densities. Combined with the doping levels, we have the reality. Okay, now you know this current density, you know this current density, so you know both current densities by calculation, and if you sum them up, you get the total current. And this total current is constant throughout the PN diode. And this value, for sure, I have calculated in the spreadsheet also. This value is ta-da-ta-ta. Where is it? I'm looking with a very small glass on the big sheet. I'm waiting for changing the zoom level. Here we are. I have plotted now diode current, not the current density, but now the current. But how? What is the difference between density and the current? It's the area. So I have taken 1 square centimeter diode, 1. And the resulting current now, as a function of the voltage, is this curve, what you know from real measurements. But it is completely calculated in the spreadsheet based on mobility, lifetime, doping concentration, on all these equations we have learned up to now. So this is the theoretical level of the current of a diode you are producing on 1 square centimeter with a doping level of 10 to the power of 16. That's it. And the rest are parasitics. Okay, so you have to start designing these devices at some point, and this is the starting point of your design. Let's go back to the slides. Now we have the sum of this value, and the sum of this value is the total current times the area. And this equation we have just taken a look in the spreadsheet. And what you know as a saturation current, IS, is now this complete current equation. The diffusion level, diffusion coefficient of the electrons, diffusion length, diffusion coefficient, diffusion length, minority carrier concentration. So all are parameter devices times the area is the current. So that's it. So the reason for the exponential increase is this exponential value. And the reason for this exponential decrease is this barrier decrease. And the increase of this concentration exponentially is is this Boltzmann approximation. And the basis for the Boltzmann approximation is the Fermi-Dirac statistics. So due to the Fermi-Dirac statistics curving shape, we have an exponential um, current increase with the voltage in the diode. So therefore, we have e to the power of something. Okay? So this linkage I wanted to set into your mind at least once. Okay, let's go back to this slide here. And now let's plot this. Oh, before we plot, I'm a device designer. Okay? I'm a device designer. I have a silicon. And what should I change if I want to have more current? Okay, the dumb answer is make it big. Okay, or make it more in the minority carriers. More minority carriers, more IS. Or reduce the diffusion length. A moment, how I can reduce the diffusion length? The diffusion length has the diffusion coefficient and the lifetime. Reduce the lifetime by traps so that they recombine faster. Reduce the diffusion coefficient. One moment. Reduce the diffusion coefficient doesn't work. Because here you have it under the square root. So reducing the diffusion coefficient doesn't work. Because it also counteracts in the understanding of the diffusion coefficient, because it's the mobility times whatever. So you have to increase the mobility so they can move faster and increase the current. Okay, so these are some teasers to think about how diet does work. Okay? And plotting these equations, so the saturation current, I have copied here again. And we see that in the reverse polarity, so here in the reverse polarity, the current at 0 volt is 0 and it is constant. This constant value is the saturation current. We can't avoid. And now the current increases exponentially from 0 volt on, not at zero point 0.7 volt. No, from 0 volt start the current does start. And it increases exponentially. An exponential increase plotted logarithmically, it is an constant slope. Okay, but we are differing from the constant slope because we have -1. Oh, someone has fallen out of the connection. Many people have fallen out from the connection. Uh-oh. Okay. So some have trouble. We are at the end of the lecture, so they don't have to worry. So from this slope, we can extract the saturation current of the diet, or we can measure in a reverse direction and we can extract the saturation current. But in the measurements, we have all the leakage currents, all the non-idealities in the value, not only the expected theoretical value. Okie dokie. So here we are with the PN diet. And next week, one moment. Next week, we will take a look at the parasitic properties of the PN diet concerning the capacities and also the differential resistance of the diet, which is very important for the analog circuit generation and the behavior of the diet for small signals. So that's all for today. I set here finite. See you next week. Bye bye. Ciao. So